I'm Besim Dragovic, and I have a PhD in Earth Sciences from the Department of Earth and Environment at Boston University. I call myself a geochronologist, so I think about the timing of geological processes, the rates at which those processes occur, and this could be on the order of, say, millions of years to weeks and months. I think largely about two areas. One is how elements and water and such cycle through the Earth on a global scale. All right, so when water starts in the ocean floor, or in the oceans, it starts to make its way, they get subducted eventually and make their way into depth. And this is a place where this water is a place where there's a lot of cycling that goes on. When rocks get buried down that deep, they start to dehydrate and lose their water. So a rock that looks like this, we call this rock a serpentinite. This would have been something that was sitting on the ocean floor for hundreds of millions of years. When you bring this down to depth, you end up dehydrating it and sucking all the water out of it, and you suck as much water out of a rock of this size that's enough water to fill this coffee mug. And the implications of that are vast. That water seeks to melt rocks and create volcanoes, like we see in Japan, like we see in Tonga recently. It creates earthquakes as well, but it also carries all elements with it and volatiles with it. So there's this large-scale recycling of water and other elements that happens over geological timescales that has lots of implications for things like how the atmosphere was formed, how life started in the first place. Which leads to the second thing I think about is when in the world did processes like this start happening on Earth? So I look at really old rocks from, say, billions of years ago, 2 or 3 billion years ago. We call these places cratons. And they give us this clue as to not only when geological processes that we see today started, but what are the implications for that on early life, on early oceans, early atmosphere. So I teach 3 courses largely, or 3 of the courses I do teach. One is Introduction to the Earth, which is the introductory class, the geology class that the SEOE offers. And it's largely for non-majors, but we do get majors peppered in there. And I love that course. It's my favorite course. And it's my opportunity to teach kids about probably some stuff they haven't heard, at least in a while or very little. So it's my opportunity to get at the students and teach them about how the Earth works, how the Earth and environment work. And so it's my favorite class by far. The other class I teach is an upper-level undergraduate class called Igneous and Metamorphic Processes, and we talk a lot more about deeper Earth processes and how the Earth works at that kind of global scale, and how the solid Earth works, and what are the processes that happen in the solid Earth, and how do they interact with the oceans and climate as well. And then the final class I teach is a graduate-level class called Isotope Geology and Geochronology, and this is an opportunity for the graduate students to learn more about radioactivity, how we use isotopes for things to understand low temperature processes in the oceans and atmosphere, but also how to date beautiful rocks like this, and what do we use those techniques for thinking more about Earth processes and the rates of these processes. I have a number of students who work in and out of the lab. I currently have 3 graduate students who work here, 1 master's and 2 PhD students. I also have 2 undergrads working here and 2 postdoctoral students working as well. And they work on a variety of things related to the topics I just talked about. But it goes anywhere from students, here one anecdote is I have an undergraduate student in middle school education who's in the College of Education. And she came up to me after the course I taught and said, I want to do some research. And I said, well, you want to date a rock? And she was like, of course I do. So now she's trying to date her first rock. And I think this will be a really nice, she finds this to be a nice experience wherein she can go back to her middle school science students and say, look what I was able to do some lab work and date a rock. And I think that makes me really happy that she's able to have that experience. Students do anything from a lot of lab work to field work. So I have students working in Montana, students working in Canada, students working in the Alps, Switzerland and Italy. So there's lots of opportunities for both field and laboratory work. I was in industry for the longest time. I did a lot of cement and concrete research initially, and I did that for years before I went back to graduate school. And I fundamentally loved geology. My most influential teacher in high school was my earth science teacher, astronomy teacher, and his name happened to be Mr. Block. And he really made me love geology and understanding how the Earth works and trying to be an Earth historian. And so I wanted to pass that on to students, but I also loved doing the research. I loved science, I loved math, And to be able to pass that information on to students, particularly at the 101 level, the Introduction to Earth level, was just always, it was just too tantalizing for me. Yeah. Students should study in the SEOE because one is because of the diversity of disciplines that we have here. So there's lots of opportunities for students to learn about environmental policy, environmental science, ocean and marine sciences, and geological sciences. And I think students can learn how the earth and environment and the oceans work, but we also want students to be its best stewards and its best managers going forward. And I think that's the role that the earth and environmental sciences plays these days. It's not just understanding how the earth and environment and the oceans work, but also how we can be its best stewards. And I think that's the value of an undergraduate degree and a career in the earth and environmental sciences.